Good afternoon. Welcome to this special session from Nehru Planetarium Museum Library to celebrate and to place in perspective for everyone the very exciting fact of the Nobel Prize going to black holes this year. And to put this in perspective, take us through for a black hole walkthrough. We have with us Professor Patrick Das Gupta from Department of Physics and Astrophysics, Delhi University. He will take us through a very user-friendly walkthrough of the same. And I request you, Professor Patrick Das Gupta, to take us through this walkthrough.
Thank you very much, Dr. Ratnashri. So it is, in fact, very exciting for all the physics community who are working in the field of black holes and in general in the field of general relativity. All right. And now we go through the slides to essentially pay tribute to the three physicists who gave observational evidence and theoretical evidence for the existence of these singular objects that are sheathed by a mathematical surface called event horizon. So Professor Roger Penrose, who did pioneering work in 1965 to show that general relativity predicts that when you have an object collapsing under its own weight, then under very general conditions, such a gravitational collapse would lead to singularities. We will discuss what singularities mean. And then the astronomer from USA, Professor Andrea Ghez, she and Professor Reinhard Genzel from Germany, they independently observed the region very close to the center of Milky Way Galaxy using innovative techniques like adaptive optics to have fine resolution of stars moving around the galactic center, and thereby provided very strong evidence for the existence of a million solar mass supermassive black hole at the center of our Milky Way galaxy. Right. So now let's go ahead further. And this is the slide that describes the Nobel Committee's citation for the 2020 Nobel Prize in Physics for these three outstanding physicists. All right. Right. But it all began in 1915 when Albert Einstein succeeded in giving a theory of gravitation that is consistent with the tenets of special relativity, that says that no effect can progress from a cause with speed faster than the speed of light. Newtonian gravitational theory was action at a distance. So if you change the position of the sun now, the change in the gravity felt by our planet or for any other planet will be instantaneous. And such an instantaneous cause and effect relation is prohibited by special theory of relativity. And what Albert Einstein realized, that because gravitational acceleration of a test particle doesn't depend upon the mass of the test particle. This was originally discovered by Galileo from his famous experiments from the top of the Leaning Tower of Pisa. And Einstein immediately realized that this fact, that gravitational acceleration of a test body is independent of the mass of the test body, he realized that gravitation, therefore, is not a force, rather, it is the non Euclidean nature of the geometry of the space time. And furthermore, because his general theory of relativity is a relativistic theory of gravitation, and therefore, mass as the source of gravity in Newtonian theory gets generalized to energy and momentum of matter. That is the source that distorts space time geometry. All right. And because every particle, or for that matter, every wave, is associated with energy and momentum, and therefore every entity in the universe would cause the geometry of the space time to be warped according to the theory of general relativity, and thereby, indeed, gravitation is universal. That is, everything causes gravitation. All right. Now, uh, Einstein, of course, realized from this Galilean equivalence principle that if you have uniform gravity, what do I mean by uniform gravity? If you have a situation where not only the magnitude of the gravitational field, or equivalently the gravitational acceleration felt by a test body, so if the magnitude of the gravitational field is constant everywhere, and so is the direction, then we say such a gravitational field is uniform. And Einstein realized that uniform gravitational field is actually equivalent to no gravity. How is that to be explained? Imagine that you have uniform gravity everywhere. Then consider an observer who is in a large frame of reference. And if this large frame of reference is let to freely fall, okay, if it is freely falling in this uniform gravitational field, then for the observer in the freely falling frame of reference, gravity doesn't exist. Why? Because if this freely falling observer drops any object or throws any object, for the freely falling observer, the object that is dropped will just hover near him, and it will be essentially at rest with respect to him. An object thrown by him, for an outsider, uh, the object will be uniformly accelerating, but for the observer who is free falling, the thrown object will be moving with a uniform velocity, and thereby the freely falling observer sees no gravitational force, and hence he or she will conclude that there is no gravity. So, in other words, uniform gravity is no gravity, is equivalent to no gravity. And what Einstein established is that true gravity is actually is essentially the tidal force that's predicted from Newtonian gravity. As we know that if you have a point mass m, then the gravitational field, according to Newton, due to the point mass, its magnitude, of course, it's attractive. The magnitude is gm by r square at a distance r, and because this gravitational field is distance dependent, and therefore different points at different distances will encounter different force, and therefore if you have an extended body like earth with its ocean seeing such a point mass, different parts of earth and ocean mass will see different attractive gravitational force, and therefore will suffer a differential change or extension. And in fact, precisely the tides in our ocean is due to the differential gravity seen by different points on the Earth due to sun's gravity. And the tidal acceleration is proportional to g times m divided by the cube of the distance, where g, of course, is the Newtonian gravitational constant. In fact, this tidal force leads to many fascinating phenomena, like, of course, high tide and low tide, but why the moon always presents the same face as it goes around Earth, and so on. And from general relativity, there are many unique predictions. For example, general relativity predicts that when an object is collapsing, a collapsing object leads to trapped null surfaces. In fact, Penrose was the person to talk about trapped null surfaces and then event horizon and eventually singularities. Furthermore, general relativity also predicts gravitational waves because it is a theory which is consistent with special relativity, and therefore, any disturbance in the gravitational effect can only propagate at the most with speed c, and such propagation of disturbance in the space time geometry is what are called gravitational waves. And we know that direct detection of gravitational waves was made around 2015 due to the LIGO observatory, and because of which Kip Thorne, Ray, and uh, another physicist, they were awarded the Nobel Prize. Now, general relativity, of course, is a nonlinear theory, and that is the reason uh, not many exact solutions are known for general relativity. There are just a handful of exact solutions from general relativity. In fact, a two body system which is dynamically evolving, there is no exact general relativistic solution for such a two body system which is dynamically evolving. So, therefore, one expects that in future, this nonlinearity of general relativity would cause a lot of surprises. And indeed, it's an exciting area of research. Right, let's come to the Nobel Prize work associated with Roger Penrose. Now, in 1955, it is the work of late Professor Amal Raychaudhuri, who used to teach in Presidency College, now Presidency University. His work in 1955, which is sort of christened as Raychaudhuri equation, that was instrumental in the singularity theorems which were proved by Penrose and Hawking in mid 1960s. And of course, Chandrasekhar's work around 1930 showed that indeed objects with mass greater than a particular critical number cannot be stable, and they necessarily have to shrink. And Chandrasekhar's work paved the way for black holes being just mathematical curiosity to the possibility that indeed black holes can form under astrophysical circumstances. Right. The early men of black holes, you'll be surprised to know, uh, are Michel and Laplace. Michel and Laplace, they used Newtonian gravity arguments to show that there could be objects from which even light can't escape. I'll talk about it in my next slide, but let us also go through the early men of black holes post general relativity. So, as soon as Einstein published his work in 1915, giving the first correct theory, relativistic theory of gravitation. Within few months, Carl Schwarzschild, he gave an exact solution. He considered a spherically symmetric mass and worked out the exact general relativistic solution outside the spherically symmetric mass and got an exact solution. This solution today we refer to as Schwarzschild solution. And Carl Schwarzschild also realized that such a solution has a very peculiar situation if the entire spherical mass shrinks below a particular radius, today called the Schwarzschild radius. The next black hole solution was given by Roy Kerr in 1960s. He considered a rotating object, that means not spherically symmetric but axisymmetric object, and outside such an axisymmetric object he found out an exact solution. And such an axisymmetric object, if it collapses, it leads to what we call the Kerr black hole. And Chandrasekhar, in his mathematical theory of black holes, pays a, big tribute to Roy Kerr in establishing the Kerr solution. Later on, charged black holes were considered by Reisner and Nordstrom, black holes which are not only electrically charged but rotating black holes as well. Similarly, in 1947, S.D. Majumdar and independently Papapatro, they obtained an exact solution of multi-charged black holes in a static space-time. Basically, these multi-charged black holes, they maintained a static configuration because the electrostatic repulsions, they balanced out the gravitational attraction. So remember, although it's a multi black hole solution, exact solution, it's a static solution, it's not a dynamic solution. Then, of course, there is another great exact solution due to the work of late Professor P.C. Vaidya, who obtained a solution in which you have an object that is spherically symmetric, out of which zero rest mass particles are being emitted radially outwards. And such an exact solution has been named after the discoverer, namely, they are called Vaidya solutions. Right. Now let us look at the artist's conception of our Milky Way galaxy as seen from a side view. So if you look at our Milky Way galaxy edge on, of course, we can't do that because we can't go out of the Milky Way galaxy with our existing technology. And that's why this is a cartoon made by an artist based on astronomical observations. And you can see that our Milky Way galaxy is a disk galaxy with a prominent bulge around the center, and the spiral arms are located in the disk region. And our solar system is about 8,000 parsec from the center of our galaxy. One parsec is 3.26 light years, or in other words, one parsec is 3 times 10 to the power 18 centimeters. All right. And our solar system is going around in roughly a circular orbit. Of course, it is also bobbing up and down perpendicular to the disk, but it is also going around in a circular orbit around the galactic center, just like most of the stars which are located in the disk of our galaxy. On the other hand, the stars in the bulge, they go in eccentric elliptical orbit around the galactic center. And from the work of Professor Reinhard Genzel and Professor Andrea Ghez, we know that indeed at the galactic center, which is called Sagittarius A star, there lies a supermassive black hole which is 4.5 million times heavier than Sun. Remember, Sun's mass is 2 times 10 to the power 30 kilograms. So, in astrophysics and astronomy, the scales are indeed astronomically large. Right. Now, the question is, if there is direct evidence of black holes possible, how would we get direct evidence? These are, of course, indirect evidence. But let's go into the Michel and Laplace's argument, which are quite simple as to how we can have objects from which even light can't escape. Imagine you are on the surface of a spherical object of mass capital M and radius capital R. All right. You can, at the back of your mind, you can think of this object as Earth, but it need not be Earth. It can be any generic spherical object of mass capital M and radius capital R. And let's say you want to throw object, throw an object such a way that object doesn't come back. We know that when we throw cricket balls or any object upwards, eventually it comes down. But suppose you want to throw an object with initial speed from the surface, initial speed v, and you ask, what should be the minimum speed with which you should throw the object in such a way that it never returns to this huge spherical body? The answer is very simple. After all, we know from Newtonian physics that any object at a distance d from the center of this massive spherical body has a gravitational potential energy minus g capital M by d, where d is the distance from the center. And this is the gravitational potential. But if the test particle has a mass small m, then the test particle's potential energy due to gravity, Newtonian gravitational potential energy due to this massive object, is minus g capital M small m divided by d. Okay. And in particular, if the object goes to infinity, d becomes infinity, and therefore the gravitational potential energy at infinity is simply zero. So as the object comes nearer and nearer, the gravitational potential energy becomes more and more negative. In particular, if the object is on the surface of this massive body, then the gravitational potential energy of this test particle is minus g capital M times small m divided by capital R, because the object is now at a distance capital R from the center of this massive object. And let's come back to the problem. You want to throw this test particle with a speed v such that it barely escapes to infinity. So if you throw it with speed v, it also has a kinetic energy. So therefore, the total energy of this test body will be the kinetic energy half small m v square, where v is the initial speed, plus the gravitational potential energy, which is minus g capital M small m divided by r. And you want that the object, when it goes to infinity, it barely goes to infinity. That means when it goes to reaches the infinity, it shouldn't have any speed. because we know as the object goes upwards, its speed v keeps on decreasing because the total energy has to be conserved. And as it goes up, gravitational potential energy increases, and therefore kinetic energy must decrease. So if you want the test body to barely escape, then at infinity, the total energy must be zero. So in other words, you must throw it with the speed v such that the total energy, half mv square minus gmm by r, is equal to zero. Immediately from this equation, you see that you get the escape speed v is equal to square root of 2g capital M divided by capital R. Now this calculation, all of us do it when we are studying in school, all right? And in fact, we know that for Earth, such an escape velocity has a magnitude of about 11 kilometers per second. And if you take this expression 2gm by r, plug in the value of Earth's mass for capital M and about 6,000 kilometers for Earth's radius, you will get the value about 11 kilometers per second. What Michel first asked, followed by Laplace, was, can the object, the massive body, shrink to a radius such that the escape velocity becomes speed of light? So in other words, Michel and Laplace were asking the question, what is the value of the size of the massive body so that the escape speed becomes speed of light? So if you put c is equal to square root of 2gm by r, immediately you can see the massive body must have a radius rs equal to 2gm divided by c square. In other words, if the spherical massive body shrinks to a radius rs equal to 2gm by c square, then only light can escape from the surface of such an object. No other, no slower object can escape from such an object. And immediately they realized that there's a funny thing that is happening, that if r becomes less than, that means size of the massive body becomes less than rs, then even light can't escape from the surface. So therefore, that object for an outside observer will appear dark because even light can't escape. And today we know from special theory of relativity that no particle can move faster than the speed of light because of the fact that the relativistic inertial mass is equal to the rest mass divided by square root of 1 minus v square by c square, where v is the speed of the particle. And if you put v greater than c, then you get imaginary number. And the rest mass or rest energy or relativistic energy cannot be an imaginary quantity. All measured quantity in the universe are real number, and therefore, since no particle can move faster than light speed, the moment an object shrinks to a size less than 2gm by c square, it will become a dark object. Now, this was established using purely Newtonian gravity. And the surprising thing is that Carl Schwarzschild, using the actual relativistic theory of gravitation, namely general relativity, got the same result. That means for the spherically symmetric object, the fact that if a massive spherical body shrinks below the radius 2gm by c square, it becomes completely dark, is a conclusion that is true not only in Newtonian gravitation, but is also true in general relativity. And to pay tribute to Schwarzschild, this radius 2gm by c square is called the Schwarzschild radius. Right. So far, what we have established that in even when you take general relativity um, as a theory and calculate using the Einstein's general relativity the solution outside a spherically symmetric object, then you find that if the spherically symmetric object shrinks below the Schwarzschild radius 2 gm by c square, it turns completely black. And this mathematical surface with a radius 2 gm by c square is called an event horizon. The reason is very simple. Why is it called an event horizon? Because any event that is taking place below the event horizon can never be seen by an outside observer. The reason being that any event that is happening in the interior region, if a light is emitted from that event, the light cannot come out of the event horizon, as we have established using Newtonian argument. Therefore, the outside world will be completely oblivious to what is happening within the event horizon. In fact, when a spherical body is collapsing to form a black hole, the outside observer will never see the collapsing object ever to shrink below the event horizon. But that doesn't mean that the black hole doesn't form. It forms because if you are a freely falling observer, unfortunately, if you are a freely falling observer with the collapsing object, then you will see that the matter is collapsing within a finite time. All matter collapses and goes to a point, including the freely falling observer, so that this point, entire mass goes into a single point. And when entire mass goes into a single point, the density becomes infinite. And whenever in physics any quantity becomes infinite, we say it is a singular point or there is a singularity. Why? Because in physics, all laws are expressed in terms of differential equation. And in order to solve differential equations, we need initial conditions or boundary conditions. But if something becomes infinite, infinity cannot be an initial condition or a boundary condition. So when there are infinities for physical quantities, you cannot evolve such initial condition using your dynamical laws, namely which are in the form of differential equations. And hence, your theory breaks down if physical quantities become infinite. In general theory of relativity, yes, the density becomes infinite, but the geometrical quantities which define the space-time geometry, which are essentially related to the tidal field, okay, they are also singular, also become infinite at this r equal to 0. They are called Riemann curvature tensor. The components of Riemann curvature tensor defining the non-Euclidean geometry of the space-time, they also become infinite at this r equal to 0. That's why the r equal to 0 is called singularity. All right. Now, let me not, I have already talked about all this. There is another very nice analogy for the event horizon, and I have taken this slide from Dr. Strassler, published in 2014. And the slide talks about a river moving along a slow downward slope, reaching a precipice and eventually going down in the form of a waterfall. Now we know that when the river is going downstream, the central region of the river will be moving faster than the portion of the river adjoining the banks of the river because of the viscous drag felt by the water and the solid uh, objects lying at the banks of the river, and therefore there is a velocity gradient. Central portion will be moving faster, and the river velocity near the banks will be slower. So in particular, uh, if you consider the a particular velocity, let's say 100 miles per hour, just a fiducial number. So take the following speed, 100 miles per hour, and let's say the center of the river attains this velocity 100 miles per hour at this point. Of course, the river velocity is increasing as you go towards the right, towards the precipice. And you find out what are the other points where the water speed is 100 miles per hour, and you will get such a locus of points. So these dotted lines form the locus of points where the water speed is 100 miles per hour. And as I said, the reason why uh, you have such a locus, because the central speed is higher than the speed at the bank. So at this point, the bank speed is smaller. So if you want the speed near the banks to be also 100 miles per hour, you have to go further down hill, okay, further downstream, right? So this dotted line, the locus of dotted lines, indicate where the water speed is 100 miles per hour. And let's say I am having with me a motorboat where the engine is such that the maximum speed of the motorboat with respect to water is 100 miles per hour. All right. Then you can immediately see that if I am moving uh, in this motorboat in the river, then I can move backwards and forward as long as I don't cross this dotted line. The moment I cross this dotted line, because if I want to go back with respect to water, I would be moving with 100 miles per hour when the engine is in full throttle. But for an observer at the bank, because the water is moving with a speed towards right faster than 100 miles per hour in these region, for him, my speed will be essentially 100 miles per hour minus the speed of the water, and therefore it will still be negative, and he will see me moving towards the precipice and eventually going down the waterfall. Okay, so therefore this dotted line is like an event horizon for all observers with motorboat having a highest engine speed of 100 miles per hour. Of course, if your speed limit increases, you can go closer and closer to the point of the waterfall. But this essentially gives a nice idea of the event horizon. This line acts as an event horizon. But of course, technically, if you talk about event horizon, now remember this diagram on the left is a diagram which has been taken from Penrose's paper published in 1965, where he showed how black holes, uh, how singularities form, how event horizon form. This is a technical slide, so I will not go to the right side of the slide, which depicts the so-called Penrose diagram for a black hole. It's a bit technical, but Penrose used a mathematical device to contract the entire infinite space-time manifold into a finite set using something called conformal transformation, because conformal transformation preserves the light cone structure. What is the light cone? We know that if my time is going in the vertical axis and the space is in the horizontal axis, then the surface covered by all light rays form something like a cone. Okay, because and nothing can move faster than the speed of light. Therefore, no particle can go out of the light cone. Particles move in future within the light cone. And therefore, Penrose, he showed that when a matter, so this vertical line is the direction of time and horizontal section is space section. When matter is collapsing with time, then after some time, and you plot the light cone at various points, then you find that the objects behind are the past light cone, and the forward cone is things that are directed future. As the density of the collapsing object becomes more and more, the cone starts tilting, and when the matter crosses the so-called event horizon, the light cone, future directed light cone, completely tilts within the event horizon, and therefore any future light ray only hits the singularity, and that is how the event horizon forms. It's a technical part, but just for the completion, I have flashed. Those who are interested must learn general relativity in its full glory. I will skip this just to mention that Penrose also introduced the idea of closed null trapped region, which which essentially is a region from which is defined to be, even if you shine a torch outwards or a torch inwards, the distance between the wave fronts of the outgoing light wave front and the ingoing light wave front, they don't increase, but they keep on decreasing. That means this region is a trapped null surface. These are technical things I will skip for the moment. So I'll also skip this slide. Uh, Now, Penrose's contribution also regarding extraction of energy from a rotating black hole, uh, published in 1969, is also to be mentioned now that we are in this discussing the subject of black holes. If you take a rotating black hole, the so-called Kerr black hole, as I have already mentioned, Roy Kerr gave an exact solution in 1963. For a rotating black hole, there is, of course, a event horizon, and of course, there is a singularity at r equal to 0, but there is also a region surrounding the event horizon, the so-called gray area. It's called the ergosphere. The ergosphere property is such that although if one is moving in a spacecraft, enters the ergosphere, one can of course come out. Unlike if the spacecraft enters the event horizon, then of course the spacecraft necessarily has to go and hit the singularity. But if one is in the ergosphere, one can come out. But if one wants to stay at rest in the ergosphere, then it's not possible. The ergosphere, because of the rotation of the black hole, it'll drag the spacecraft, and one can't be at rest with respect to the distant stars. So with respect to the distant stars, a spacecraft that enters the ergosphere necessarily has to move because of the so-called dragging of the inertial frames due to the rotating black hole. But furthermore, the interesting feature of the ergosphere is that inside the ergosphere, a particle can have negative total energy as measured by an observer at infinity. An observer who are far, far away from this Kerr black hole will find a test particle if it is moving in a counterclock direction. The black hole has an angular momentum, it is rotating. So, supposing it is rotating in this direction, so that means in an anti-clockwise manner, then if a test particle moves in a clockwise manner under certain condition, such a test particle will have total energy negative. By total energy, I mean rest energy plus kinetic energy plus gravitational potential energy. This total energy can be negative. And what Penrose in 1969 had shown that using such a using the negative energy, one can extract energy from the Kerr black hole, and this cartoon shows this process. So supposing you are viewing the uh, Kerr black hole from the direction of its rotation axis, so that the ergosphere equatorial region is this, the event horizon is this, and let's say you throw an object towards the ergosphere with some speed. And let's say that object breaks up into two particles, A and B, such that B moves in a moves counter to the rotation axis of the black hole, and therefore it has a negative energy. And that can't escape out of the ergosphere, because outside the ergosphere there is no negative energy trajectory. So this will go into the singularity, but the outside particle can escape. But since the total energy has to be conserved, if the blue object which has negative energy, the red object must have energy exceeding the initial energy, because the total sum must be equal to the initial energy. If one of them has negative energy, the other must have a greater energy than the initial energy, because the sum must be conserved, and this can go out with a speed higher than the initial object that fragmented inside the ergosphere. So, this way one can extract energy out of the black hole. And where is the energy coming from? The energy is coming at the expense of the rotational energy of the black hole. The black hole, its mass decreases because the negative energy will decrease the mass, as well as the rotational energy decreases because the counter clock rotation means the angular momentum of the black hole also decreases. Right. Now we come to the observational evidence for black holes. The fact that black hole has an event horizon and anything from within the event horizon cannot escape out, and therefore classically black holes must be dark. Immediately the question then would arise that if I am peering at a night sky and I see a dark region, how do I know whether there is a black hole there or there is no black hole, there is empty space? After all, black holes also appear dark. Now, what happened in 1970s is that one X-ray source was discovered, the so-called Cygnus X1 X-ray source, and the X-ray luminosity was varying very rapidly. In fact, the time scales over which the X-ray luminosity was varying was shorter than 1 second. Later on, people also found out that this X-ray source, Cygnus X1, is a binary system where there is a normal star moving around the common center of mass, and there is a unseen primary object. It was not seen, but the fact that the secondary star was moving, immediately you could infer that there is a massive uh, object which is the primary object, and it forms a binary system. The fact is that from the variability of the X-ray luminosity, one could argue what is the size of the emitting region. How? Because if the fluctuation is over, let's say, time scales delta t, and let's say the X-ray luminosity is doubling up in a time scale delta t, that means the region which is participating in this doubling up of X-ray luminosity, something must be moving around. Let's say a new blob of emitting region must have moved towards the viewing section so that the luminosity has suddenly brightened up by a factor of 2. And if delta t is the time scale of fluctuation, clearly the movement of this blob cannot be faster than speed c, because that is what special relativity tells us. And therefore, the size over which the blob has moved cannot be more than speed of light c times delta t. So that gives us an upper bound on the size of the emitting region, which is showing this variable X-ray luminosity. And immediately, if you put in delta t to be less than 1 second and speed of light being c 3 into 10 to the power 8 meters per second, you see that the size must be less than 3 into 10 to the power 8 meters. Remember, sun's size, our sun has a radius of about 6.96 into 10 to the power 8 meter. And the mass was more than sun's mass, more than 10 times sun's mass. And yet, if the emitting region, which is outside the this unseen primary object, itself is lower than 3 into 10 to the power 8 meters, that means the outside matter itself is smaller than sun's radius, and yet the mass, unseen mass of the primary is greater than 10 times sun's mass. This object must be a very massive and yet compact object. And theoretically, such objects necessarily have to be black holes. So Cygnus X1 was one of the earliest indirect evidence of an astrophysical black hole. There are other ways of also finding out whether there is a black hole, which I will come to shortly, because that is the subject of this year's Nobel Prize. And let's go ahead. So this is a cartoon showing how blobs breaking up can cause fluctuation in the X-ray luminosity of the Cygnus X1 source. So in other words, the model is that there is a black hole and the matter from the secondary star, as it flows, because there is a rotation involved, the flowing matter, it cannot radially come in and hit the black hole. It forms a disk-like structure. Such disks are called accretion disks in astrophysics literature. Now, let's come to the Nobel Prize work of Andrea and Reinhardt. We know that stars are found in galaxies. So this is a disk galaxy with presenting an Aegean view. The disk of the galaxies is a bulge of the galaxy. Similarly, another Aegean disk galaxy or a spiral galaxy. A disk galaxy which happens to present us with its face perpendicular to the line of sight, so that we see the disk's magnificent spiral arms. Then there are other kinds of very large, massive galaxies called elliptical galaxies, which are triaxial spheroidal systems. And by now, we know that all such dominant galaxies have supermassive black holes at the center. In particular, the work independently carried out by Andrea's team as well as Reinhardt's team was to monitor the motion of stars orbiting very close to our galactic center, which is called Sagittarius A star. And they painstakingly, for more than 10 years, monitored the motion of stars around the galactic center. You can see this asterisk here. That asterisk marks where our galactic center is. And you can see that many stars, they move in highly eccentric elliptical orbit, and the closest approach distance to the galactic center can be very, very small. As you can see, this star's elliptical orbit. There's another elliptical orbit around this. These are elliptical orbit. There are, of course, some circular orbits too. And from the motion of the stars and using the eccentric orbits, they could estimate what is the mass that is causing such eccentric elliptical orbits. For a simple exercise, if you consider a circular orbit around the galactic center at a radius r, then we know that if a star has to move in a circular orbit with a radius r, then the centripetal acceleration is provided by the gravitational attraction from a mass at the center, and therefore v square by r must be gm by r square. In other words, v square must be gm by r. In other words, v is square root of gm by r. So I can monitor, from the monitoring of the trajectory, I can estimate the speed of a star moving in a circular orbit. From the position measurement, I can also find out the radial distance from the center, and therefore, using v square equal to gm by r, I can estimate the mass encompassed at the center. And using such calculations, the result that came out from Professor Andrea and Professor Reinhardt's team was that indeed the central region has a mass as large as 4.5 million times Sun's mass, but the stars going very close to this point showed that the size of an object must be even smaller than the total size of our solar system. And only objects that can be so massive and yet the size would be so small are black holes. You might say, but these are indirect evidences. How do we know that there are actual black holes? The first very strong evidence of black holes came from the direct detection of gravitational waves from black hole binary mergers. And here is one of the recent gravitational wave event that took place on 21st of May 2019, the so-called GW 190521 source, where if you analyze the gravitational wave signature, you find that the objects, the binary object, one had a mass 85 times sun's mass, the other was 66 times sun's mass. As they moved around the common center of mass, they emitted gravitational waves and thereby lost energy, and hence the orbital size shrank, and eventually they formed a very massive black hole. So they coalesced to form a very massive black hole weighing 142 times sun's mass. You might say that the total mass was 151 solar mass. Where has the rest of the mass gone? They were essentially carried away in the form of gravitational waves, because we know energy is equivalent to mass. So the gravitational wave energy that escaped carried away the rest of the mass. All right. And how do we know that they are black holes? Because if the black holes, if there were any other object of 85 solar mass and 66 solar mass, the size would have been much bigger. And therefore, when they came close to each other, they couldn't have come very close to each other because their sizes was larger, and such object frequency cannot be higher than a particular value. But these gravitational waves were of very high frequency, implying that these two objects came very close to each other, like black holes could, because the event horizon sizes are smaller. And furthermore, the fact that no other optical counterpart or electromagnetic counterparts were seen also implies that they were not normal stars, because normal stars, as they collided, they would have also left behind electromagnetic signal. But there was only gravitational wave signal, showing that indeed these were black hole binary mergers. The other evidence, of course, is the recently observed the so-called silhouette of a supermassive black hole in the center of M87 elliptical galaxy, and the light that one sees are basically the light coming from matter swirling around the black hole. But you can ask, from how close can you still see the light? And that region is called photon sphere, because a photon can be in a circular orbit around a black hole at a, if the black hole is Schwarzschild black hole, at a radius which is 1.5 times the Schwarzschild radius. No photon below 1.5 Schwarzschild radius can be circling around the black hole, and thereby coming out, they necessarily have to go inside, and therefore the inner outline gives us the size of the photon sphere, and it indeed agrees with the independent mass evaluation of the M87 supermassive black hole. And therefore the Event Horizon Telescope data gave almost direct evidence of a black hole. Now have already crossed the limit, but I will just take few minutes to summarize what I have stated. So remember that very direct evidence of black hole is not yet there. How would you get a direct evidence of a black hole? There are three ways. One is that there was a work done by late Professor C.V. Vishweshwara way back in 1970. In fact, we are talking about this work 50 years hence. And Vishweshwara showed that if you perturb a black hole, then the event horizon sort of oscillates. It rings like a bell, and it has a characteristic frequency. So gravitational wave signature would have this ringing mode coming out of the perturbed event horizon, and there is certainly evidence from the LIGO detection that one is seeing such quasi-normal modes of a perturbed black hole, but the statistical significance is still not very high. Once the sensitivity of LIGO detector becomes high enough so that at 99 confidence level, we can say that we are seeing this ringing mode of a perturbed black hole, then that would be indeed the direct detection of black hole. The other way to see whether the signal one is getting is from a black hole is use the Penrose method of energy extraction. So if one can see the Penrose process directly, because Penrose process relies on the existence of negative energy inside the ergosphere that can only happen in the case of a Kerr black hole. So in future, if astronomers detect the energy extraction via Penrose process, that would be a direct detection of a black hole. There is a third detection, which is what Hawking predicted in 1974. He started doing quantum analysis around the event horizon, and we know in quantum mechanics we have the energy and time uncertainty relation delta E into delta T greater than about Planck's constant. So from vacuum itself, one can produce virtual pairs of photons, virtual pairs of electron and positron. And if one of the partners fall through the event horizon, then it cannot reunite it back with the other counterpart, and therefore the other counterpart can escape. And Hawking showed such escaping particles would have a black body temperature. And so indeed, quantum effects tell us that black holes can emit like thermal black body. The event horizon would be like a thermal black body. Unfortunately, Hawking's work shows that the black hole temperature, this is the expression that Hawking derived, the black hole temperature for astrophysical black holes is very tiny. So, for example, if our sun is to become a black hole, the event horizon will have a temperature only of the order of 10 to the minus 7 degree Kelvin. These are even cryogenics, getting such temperature in our cryogenics lab is very hard. So, in other words, Hawking temperature so far has not been directly seen. If it was seen, then Hawking surely would have been given a Nobel Prize long time back. So, it is really unfortunate that Hawking is no more with us. But detection of Hawking temperature is another will be another direct evidence of black hole. But this whole field has a lot of exciting work. Unfortunately, I don't have time to discuss with it. Maybe if there is a question later, I can talk about it. So thank you for your patience. If there are any questions, you can ask.
Yeah. Thank you for that black hole walkthrough. There are a lot of questions, and some questions Kishalai Chaudhary has been very patiently answering. Thank you, Kishalai. And we will, what I will do is flash the questions on the presentation and on the screen. And if you would come to the studio tab, you would be also able to see. And I'm going to go from the latest backwards in time. Are you able to see the question on the? I will also read it out. Are you able to see the question in the window? If you come to the studio tab,
Yeah.
Megha Joshi has asked that black hole were to be made of completely antimatter, then would all phenomena remain the same?
Yes, because so long as the remember, long time back it was shown that the black hole remembers only three things. A black hole is totally characterized by its mass, angular momentum, and charge. In fact, that is the reason why uh, Subramanian Chandrasekhar, one of the greatest astrophysicists, described black holes as the perfect macroscopic objects because macroscopic objects are very large, just like astrophysical black holes, and black holes require only three numbers to completely describe them: mass, the spin angular momentum of the black hole, and the charge. So, therefore, whether you form black holes out of normal gaseous atoms or from neutrons or from neutrinos, it doesn't matter. The black hole will not remember whether it is formed out of normal gaseous matter, neutral gaseous matter, or neutrinos, neutrons, or photons. It will simply not remember. So, antimatter, as long as you take anti-hydrogen gas, which are neutral. So if you make a black hole out of anti-hydrogen gas, it'll be same as black hole made out of hydrogen gas. All right.
There was this question into which I think there was a reply also from. Uh, I'm sorry, there has been a bit of a mistake in flashing, but the question was about how many there may be in a galaxy, and I think Kishalai was suggesting that this may be also one source of error in measurements. I'm
Sorry,
guessing that
what?
this was.
What is the
The
question?
question was how many black holes will be there in one galaxy,
Well,
and I'm
as
just
I said,
guessing that this
all
is.
major galaxies that have been studied by astronomers have at least one supermassive black hole at the center. But a few years back, there is evidence of an elliptical galaxy
Oh, okay,
which has
okay.
a binary supermassive black hole. That is, two supermassive black hole going around the common center. So there are such cases where there are binary supermassive black holes
All
in the
right.
galaxy.
And so, okay, it's taking me a little time to flash some of the questions. So let me just take those which haven't been answered, just to be sure, and then we'll come back to those which have also been answered for further discussions. There was one from Gitanjali Sethi.
Yes.
Uh, why did the? I mean, I think this must be with the process, Penrose process. Why is the splitting taking place, and why do you expect one to fall inside?
Yes. So, good question. So, splitting is arranged by the observer. So, for example, we know that if I take a uh, sort of man made contraption which is weakly bound, then as it goes through the uh, ergosphere, you can have the contraption device so such a way that inside that contraption there is a tiny explosion where one object goes with an angular momentum counter to the angular momentum of the black hole. The other, therefore, goes in the opposite direction, therefore, has the angular momentum in the same sense as that of the black hole. And therefore, you can arrange the objects to have opposite angular momentum so that one object will go into the negative energy. So, in other words, Penrose process can be used by human civilization to mine energy by constructing such breaking up devices. But you can ask, can it happen in nature automatically? The answer is yes. If you have a star going towards a black hole, we know that tidal force will make the star split because tidal deformation takes place. So, a big star, if it suddenly enters the ergosphere, the tidal force can split this star into two objects. And if one of the object gets a angular momentum counter to the angular momentum of the black hole, it can go into a negative energy solution, negative energy trajectory, and thereby the other fragment can escape out of the ergosphere. The reason why the object that goes into the negative energy trajectory inside the ergosphere necessarily has to go into the event horizon, go through the event horizon to reach singularity is as follows. Only in the ergosphere you can have negative energy solution. So therefore, this object cannot go out of the ergosphere because outside the ergosphere there are no negative energy world lines. So this object necessarily has to move within the ergosphere. But as it moves, it will emit gravitational waves because the mass quadrupole tensor is changing with time, and thereby as it emits gravitational waves its orbital parameter will shrink and it will essentially enter the event horizon, and therefore it'll go and hit the singularity.
There is a query from Kishalai. Physical meaning of negative energy is non-existent, so the total negative energy has to do with the difference in directions of angular momentum and the gain loss of mass, right?
No, no, that's not true. Negative energy certainly has well-defined is a well-defined concept in theoretical physics. Remember, this negative energy is as measured by an observer at infinity. So, an object, a test particle going into the ergosphere and thereby attaining a negative energy trajectory, you can ask negative energy, who is measuring the negative energy? Not a local inertial frame. Local inertial frame will always measure the energy of the test particle to be positive. This negative energy is as measured by an observer who is sitting at infinity, very much far away from the black hole. Now, negative energy is well defined in physics. After all, when Dirac gave his equation, the so called Dirac equation, one of the reasons why antimatter particles were predicted by Dirac were the so called existence of negative energy solution. Later on, of course, in the quantum field theory, it turned out that you need not invoke negative energy solution, but a negative energy solution has no problem in physics.
There are two questions related to ergosphere. Maybe let me just uh, flash both of them. Krish is asking if it enters
Yeah,
into the
so yeah,
ergosphere.
yeah. As I answered,
Yeah, yeah.
Dr. Gitanjali
Right.
said he had asked, and I said
Yes.
that the negative energy trajectories are there only inside the ergosphere. So if a particle gets into a negative energy trajectory in the ergosphere, it can't come out because outside there is no negative energy solution. So it just can't come out. The energy is conserved. Remember that.
So that answers the other question also related. Okay, now I'm getting a little. Let me just look up the latest questions now. I wanted to go to some of the earlier questions, but I'm now coming to the latest questions which are there, and I'll try to. I hope we can be there. There are many, many questions.
Yeah, I can see one question from Tanmay Samayar
Yes,
about
yes, that was in two
formation. Uh,
comments. Yes.
it is not the immense energy in the black hole that causes the so-called virtual particles. See, virtual particles are being created everywhere because of the fluctuation of fields in the vacuum. For example, you might have the measured shifts of hydrogen energy levels, the so-called lamp Tetherford shifts, for which they were awarded the Nobel Prize. The shifts in the energy levels of hydrogen atoms is related to the fact that near the nucleus of an atom, the delta E into delta T greater than H causes creation of virtual pairs, in particular, creation of positron and electron pair, and positron electron being opposite charge particles, they are like electric dipole, and this causes a polarization, vacuum polarization around the positively charged nucleus that shields the positive charge of the nucleus as seen by the electrons, and therefore the energy levels shift. And these are measured fact, and that leads to the credence that indeed virtual particles are produced. What Hawking realized was for smaller black holes, the event horizon size is very small, and therefore the tidal forces, remember the tidal force expression, gm by r cube. Now, if r is of the order of horizon size, then r for a horizon is proportional to mass of the black hole. So gm by r cube is proportional to g by m square. The smaller the mass, tidal force experienced will be very high. And hence, if a virtual pair is produced, the tidal force will sort of pull one particle inside, the other particle can escape. And therefore, for very low mass black holes, the Hawking temperature will be higher because the virtual pair, when in which in one particle gets drawn inside the event horizon and the other particle possibility of its escaping is very high.
Uh, there was this question, Krishna Kumar Singh asking for stellar mass black holes other than variability in non-thermal broadband emission. Uh, and I guess the recent
Yeah,
the
yeah. So this is about the blazars. Yeah, blazars also because blazars are basically active galactic nuclei where the jets, X-ray, gamma ray, optical, radio jets are almost pointing along the line of sight, and therefore you're essentially seeing the region of emission very close to the event horizon. And blazars indeed show variability time, very short variability time scale, because of which you can determine the event horizon size using the same argument that I gave for the Cygnus X1. In fact, the X-ray variability time scale for some blazars are smaller than few hours time. And few hours, how much is an hour? 60 into 60, 36, about 4,000 seconds. So variability is 4,000 second multiplied by speed of light, which is 3 into 10 raised to the power 8 into 4,000, which is 12 into 10 raised to the power 11. So, as you can see, 10 raised to the power 12 meters, 10 raised to the power 12 meters or 10 raised to the power 14 centimeter is very small. A supermassive black hole having billion solar mass has a horizon size of only about 10 raised to the power 15 centimeters. So you can see that blazar variability shows that emission region is very close to the event horizon of a supermassive black hole. So all these, in fact, were in my slides, but I didn't have the time to show all those.
Shalini has this question, and
Yeah, yeah. The question I can see: how do we experimentally know that? And well,
sorry,
positrons, as you know, the first antiparticle positron was detected in cosmic rays. And how do you detect it? If you find that, uh, if you have a magnetic field and you have a cloud chamber or bubble chamber, then if an electron enters this cloud chamber, because of the magnetic field, it will start gyrating in a particular direction. If electrons count antiparticle, namely positron, enters such a chamber with magnetic field, its gyration will be in the opposite direction because of the Lorentz force is proportional to the charge. So if the mass is identical but the charge is opposite, you have detected the antiparticle. In fact, the positron was detected in cosmic rays, long time back, because of which Blackett was not Blackett, Anderson was given the Nobel Prize. Although Blackett had discovered it first, but he had only three events. He was waiting for the improved statistics. He waited, did not publish his result, while Anderson got one event, published the result, and he got the Nobel Prize. And after that, many, many antiparticles have been observed, like antineutrons. People in the collider experiments have seen so many antiparticles. In fact, even antihydrogen atoms have been synthesized in the laboratory.
I'm now going back to the very beginning and trying to take questions from that side. There was this question repeatedly given by Ananya, and Kishalaya answered that gravity has always been there. Our discovery is only getting letting us know about it. But perhaps with this, maybe a little bit of an idea about understanding of gravitation before Einstein.
Well,
Maybe if you,
gravity was
yes,
always there. Otherwise,
yeah, it's there. That's what that
we
it
would
has
not
been
have
answered, but she has been asking it
existed
again and
on the
again.
surface of the
I
earth.
thought,
But physical laws are all there. Human
but
beings with their brain and their technology keep discovering them. The laws are already there, but
I just,
there is a progression of our understanding with the help of more mathematical development and more technological development. The understanding becomes more and more goes towards the fundamental nature, and the understanding becomes sharper and sharper. The laws are anyway there.
yeah, I
Laws
thought
are not a
you,
figment. Laws are not a figment of human imagination. Human beings are insignificant in this entire cosmos. Entire cosmos is anyway ruled by natural laws since the birth of our universe.
I thought you would want to reflect on the progress. That's why I just thought let's take that. And I
Yes,
think
the
there is a
progress
question
has
here.
been very rapid.
The question, I think they're asking whether black holes are only coming from kind of the original singularity, but there are, I mean, probably you
Really,
want to
not
tell them
really.
about the other so many
Well,
black holes which are
there are
being
primordial black
detected.
holes postulated by Hawking and Carr to begin with, and primordial black holes were created early in the universe when the universe was very dense and very hot. But the black holes we are talking about are astrophysical black holes that form out of collapse of the cores of very massive stars. Supermassive black holes, uh, their origin is still being debated. Some groups say that, like Martin Rees and many others, they say direct collapse of the halo, where there's a dark matter halo um, of galaxies. Uh, During the formation of galaxies, if the dark matter halo is completely spherical, they can directly collapse to form supermassive black holes. On the other hand, with my students, I have given some theories. My students, namely Eklavya Thareja, Fazlu, Rahman, we have worked out theories in which if the dark matter particles are very low mass bosons, mass of the order of 10 raised to the minus 20 electron volt or less, then such bosons can undergo Bose-Einstein condensation, and the Bose quantum evolution of this Bose-Einstein condensation with Newtonian gravity can lead to supermassive black holes, as shown by our group, and we have published these results. So, how exactly supermassive black holes form? The scenario is still open and it's still being researched on.
Krish and Abhiraj wanted to know what happens if one falls into a black hole. And Hemant had this question, which was answered by Kishala, as why time is slowing down as we get closer to black hole. Do you want to maybe take up these together?
Yeah, see,
And
everything
I'll
slows
just
down
dash
in.
Kishala's
Let
answer
me
now.
get you first answer. If time slows down around any gravitating object, okay? The clocks on the surface of the Earth is ticking at a slower rate compared to the clocks on board satellites that are going around the Earth. Because from general relativity, you can prove that in stronger gravity, that clocks run slower. In fact, that is the reason GPS system, they constantly need the correction, general relativistic as well as special relativistic correction for time, because Earth-based clocks are running at a slower rate compared to the clocks on board the satellite carrying the GPS, and therefore there has to be a constant correction so that GPS functions well and locates region with good accuracy. And in particular, the black hole gravity being very strong, the clocks indeed run very slowly. In fact, the clocks don't run as they approach the event horizon. So a clock which is tending towards the event horizon will appear to a observer outside not to run at all.
I'm now again coming to the latest questions. And then I'll go back to see we have not missed any. That's Krish question. All black holes in this universe die only when they have consumed all the particles in this universe.
No,
Oh,
but
sorry, sorry.
why
I
would
should I should have kept it for some more time. Yeah.
no, it's okay. But we know that universe is expanding. So when you take the supermassive black holes at the centers of galaxies, they will never merge with each other because the distance between galaxies which are not bound to each other, they are increasing with time because the universe is expanding. So the supermassive black holes, they keep on increasing in mass as they keep on swallowing the gaseous matter and the stellar matter that are present in the galaxies, and they keep on growing, and the galaxies keep separating, moving further and further away because the universe is expanding. So there will be infinity of black holes in the universe that are moving away from each other.
Here is someone's theory. Leonard Susskind and
Yeah,
Aditya
Leonard
is
Susskind.
asking
Yeah,
this.
yeah. So there is again, I had those slides, but there's no time to flash. It is related to the information loss paradox. As you know, that quantum mechanics predicts that wave functions evolve according to Schrodinger equation. So if you take a wave function, its time evolution will be given by the Schrodinger equation, and the wave function will continue to remain as a pure wave function. But Hawking's calculation shows that When a black hole forms, you can form the black hole using pure wave function. Imagine that you have a pure Bose-Einstein condensate, which is described by a pure wave function, and if it collapses into a black hole, then a pure wave function, due to gravitational dynamics, it will evolve to form a black hole. But then Hawking says that the black hole will start evaporating like a black body, thermal black body. But a thermal black body radiation is not described by a single wave function. Rather, a black body system is described by uh, a sort of collection of different wave function uh, with different probabilities. And hence, it cannot, the so-called black body like temperature, Hawking temperature of a black hole cannot be described by Schrodinger evolution. And eventually the whole black hole will evaporate into nothing because of Hawking evaporation. Therefore, you started with the formation of the black hole through one single wave function. And now, when the entire black hole has evaporated as predicted by Hawking, it has evaporated with different wave function with different probabilities. Such a thing cannot be attained by so-called unitary evolution that follows from Schrodinger equation. And this is called the information loss paradox. And a lot of people are working on it. So Susskind had talked about the complementarity principle, in which he said that, well, outside observer never sees the black hole to form because all matter for an outside observer tends to hover near the event horizon. So all the entire wave function or the information is there near the event horizon, while a freely falling observer sees the entire wave function going into the singularity. So there are two different complementarity principle. The complementarity principle says, depending on observers, you see two different physical phenomena, and then based on such kinds ideas, many people like Maldacena, Samir Mathur, Gautam Mandal, many people worked out what how to resolve the information loss paradox, and this is a highly active area of black hole physics, and there is still so far we don't know what is the uh, so-called correct resolution of the information loss paradox. There is also another firewall hypothesis in which Polchinski and his group said that, to resolve the paradox, you need a very high temperature wall near the event horizon, which will sort of uh, erase all information carried by particles trying to approach this firewall. But anyway, this area is still active as far as research is concerned. And I'm not an expert of this field, so I can't comment as to which model of information loss solution is the correct one.
This is from Shivam. Uh, it's talking of bounce cosmology.
Yeah, this is a good question. See, event horizon doesn't exist for our Big Bang singularity. The reason is, of course, the Big Bang singularity is a singularity in the past, and it is not also like uh, a standard gravitational collapse, because universe is infinite, and therefore uh, energy and momentum associated with matter is spread all over the space. It's not like a compact object collapsing. So the singularity, the initial singularity of the Big Bang universe is different. It has no event horizon associated with it. Similarly, if indeed the density of the universe is higher than the critical density, then it may happen that the universe will not expand forever, but it will collapse. Called big crunch model. And in the Big Crunch model, again, the universe would enter into singularity, but there will be no event horizon. As I said, that the universe is it doesn't have a boundary, even if it's a closed model, which where there is a big crunch. Closed model also there is no boundary, and therefore the matter is not confined within a boundary. So it will not have a event horizon, have an event horizon associated with the big crunch singularity.
Here is a question from Tanmay. It's in two parts, so I'll just flash the second part after you read this. So,
Yeah, yeah. So no, no.
so
When we say
I'll flash the
photon,
second
yeah,
part
yeah, no,
now.
no, I've read the question. The When we say photon has mass zero, it is the rest mass which is zero. But the any photon that exists, it has energy, and therefore the mass energy equivalence of special relativity tells us anything that has energy E has a mass E divided by c square. So a photon with frequency nu has energy h nu, and therefore its mass is h nu divided by c square. So all existing photons have mass because they have energy, and therefore, and bending of light is worked out in general relativity. If you want to work it out in Newtonian gravity, yes, then you can assume the photon to have a mass h nu divided by c square and calculate its Newtonian trajectory. But that's of course an approximate result. After all, bending of light can be done in general relativity without bothering about energy or mass of the photon.
Kishala had a question in the comment. I'm guessing the two are related. So, mm, binary stellar mass black hole, and then the comment which he had. Shall I flash that now?
No, no, wait a minute. The
Oh, sorry.
M87 black hole is not a binary black hole. M87 supermassive black hole is a single black hole, and its mass has been estimated by the swirling plasma that is taking place around the event horizon. And how do we know that whether this mass uh, is more or less correctly estimated? Well, the Event Horizon Telescope shows that from the photon sphere size, if you estimate the mass of the supermassive black hole, it's consistent with the estimate of black hole mass using the variability time scale, the active galactic nuclei model of radio emission, gamma ray emission, optical emission from the core region of M87 galaxy. M87 black hole is not a binary black hole, it's a single supermassive black hole.
There were several questions earlier. I think people wanting to know which is the closest black hole, and I think Ishile and maybe others also answered about the black hole at the center of the galaxy. That would be a
That's not true.
supermassive black hole. Stellar
That's a
mass black holes
supermassive
would be
black.
closer, no?
Of
There
course,
would
there are
be
a lot
some
of
stellar mass,
astrophysical black holes like Cygnus
astrophysical black
X1,
hole.
Cygnus
But
X1. They
we,
are much
yeah,
closer.
whichever is the
Supermassive
closest,
black
we
hole.
probably have to just
Yeah.
find out the
Supermassive
distances
black
and
hole
figure
is
out.
8 kiloparsec from ourselves. 8 kiloparsec is a huge distance.
Kishila is also just adding to his earlier inputs. Yeah.
No,
Mm.
no, M87 is not the only supermassive black hole. As our Nobel Prize work says, that our galactic center black hole itself is a supermassive black hole, having 4.5 solar mass black hole. M87 black hole is billion solar mass, more than a billion solar mass, about 6 billion solar mass black hole, more than 1,000 times heavier than the Milky Way galaxy black hole. But all active galactic nuclei show that they house a they each of them house very massive supermassive black hole. So black holes are ubiquitous now, associated with all galaxies, not just quasars or Seyferts or blazars.
Kamalpreet had this question. Do you need any clarifications further from her? about the question?
Well, if we are inside the ergosphere and we have not gone into a negative energy orbit, we can of course escape out of the ergosphere. Only if we enter the event horizon, we can't escape.
I don't know whether this will be a good question to end our session. Benefits of a black hole?
Well, if we find a rotating black hole not very far from the solar system, then in future through space voyage, we can use the Penrose process to extract energy from this rotating black hole, provided, of course, there's a rotating black hole near our solar system. So we can
Yeah.
actually
Yeah.
use the black hole Penrose process of extracting energy. That will be useful to humankind far in the future.
Ishila says that, yeah, he was just giving further clarification about the presence of many supermassive black holes, and probably at this point I think I have not missed any questions. But if by any chance I've missed any of the questions here, once this is, I think there was, yeah. Tejinder Pal Singh had asked whether there are any possible projects, etc. I think I may have had misputting that question. Astronomy course project in Delhi University, online astronomy course project. Um, he wanted to
What?
know whether there are any online astronomy course or project which could be taken up. There was this question from Tejinder Pal Singh, and maybe
Yeah,
with this we
the
would
question
close.
is whether you want to be uh, associated with a full official project or unofficial project. Official projects would require you to be a master student in our department. But yes, you can do unofficial projects with faculty members of the uh, Department of Physics and Astrophysics by contacting several faculty members, but they would be unofficial.
Uh, Kamalpreet had a question, but I think you answered that when you answered the Gitanjali Shetty. There is this other question from Harmeet. Mm, black holes. Now, do you want to go in that direction at all?
What?
About exotic matter, universe,
Well, it depends
when
upon what
black
you
hole.
call exotic matter. I mean, so far we have not seen any exotic matter that has been postulated, like dark matter or dark energy. As you know, there is something called dark energy, which is made up of fields or particles such that the pressure due to them is negative. So, so far, no direct detection of dark matter particles have been seen. They may be exotic, and also the fields or particles making up dark energy have also not been seen. So they are also exotic. Black holes are truly speaking not exotic because black holes form out of normal standard matter, standard elements of our periodic table, which are present in stars when they collapse, can give rise to black holes.
So I think we end the broadcast here now. If there are any further discussions, they could be taken up as comments on the YouTube video, which this will be present. And so, thank you for taking us through this exhilarating black hole walkthrough. And thank you all of you for being there and asking so many interesting questions and making this a very, very interesting 1.5 hour we have spent. So I'm ending the broadcast here at this stage.
Thank you for your patience. Thank you. Thank you,
Thank you,
everyone.
all of you, everyone. Thank you.